Hello and welcome everybody to another edition of the Sheffield Machine Learning Seminar Series, which is part of the WorldWideNeuro Forum. And we are very pleased to welcome Professor Christoph Lampert here with us today from the Institute of Science and Technology, Austria. It's close to Neuburg near Vienna. And I'm Aditya Gilra, a new lecturer and assistant professor at the University of Sheffield. And I know Christoph since I was a postdoc at. We are very pleased to welcome Professor Christoph Lampert. Just a sec. Today, this is a Institute of Science and Technology flaw because the YouTube started and it's playing in the background for me. Yeah. So it's being live streamed at YouTube, and you can also look at it later, probably. Okay, so I'll introduce Professor Christoph Lampert. He did his PhD in mathematics from the University of Bonn in 2003. And then he worked at various places. He was at the Max Planck. So first from 2004 to 2007, he was at the German Research Center for Artificial Intelligence in Kaiserslautern. And then he was also at Google for a brief while. And then 2007 to 2010, he was at the Max Planck Institute for Biological Cybernetics at Tübingen. From 2010 onwards, he was an assistant professor at the IST Austria, and from 2015, he has been a full professor there. And he has a number of awards and best paper prizes and so on. I will not go into too much detail, but so we welcome essentially Professor Christoph Lampert at the of the Institute of Science and Technology. He will speak to us today on learning theory for continual and meta-learning. So welcome, Christoph. The stage is yours.
Thank you. Thank you for the introduction. Thank you for the invitation. Yes, as Aditya said, my name is Christoph Lampert. I'm have a research group for computer vision and machine learning at IST Austria, and I will talk to you about learning theory for continual and meta-learning. So in case you haven't heard of IST Austria, we are a relatively new research institute located near Vienna that concentrates on basic research, curiosity-driven, with a focus on interdisciplinarity, covering all natural sciences and mathematical fields. And I tell you this because we are hiring on all levels, so from internships and graduate school postdocs to faculty, tenured or tenure tracks. So if you need more information, send me an email or ask me afterwards during the Q&A. So in my research group, we work on different topics of machine learning, starting with theory, in particular transfer learning and lifelong learning theory, which are also the topics I'm going to talk to you about today. We also work on models and algorithms for a range of topics, starting from zero-shot learning to trustworthy learning or continual learning. And we use learning for computer vision applications such as scene understanding and generative models. So the schedule for this talk will be a brief overview and an explanation why I will talk to you about theory. And after a short refresher, that will then lay out two recent results from our group on learning theory for lifelong meta-learning and on theory for online multitask learning. And the slides are, of course, available on my homepage if you want to look them up. So let me start by a big picture overview. So if you ask a bunch of machine learning researchers, what is the holy grail of machine learning? Why are you all working on this? You might get some kind of result that we are looking for methods of building automatic systems that learn and act autonomously. And by that, I don't necessarily mean the guy on the left, but rather the fellow on the right who has the ability to help us, for example, in our everyday chores. And to do that without us telling him every individual step of how to crack an egg. So machine learning has made tremendous progress in practice as well as theory recently. And there's a bunch of things that we already know work well. So for example, if we just want to learn a single task, then there's a standard procedure for this. We get given some kind of training data. In the training phase, we run a learning algorithm that gives us a predictor. And then in the prediction phase later, this predictor can be used to assign predictions to new data points. And since in this talk I will concentrate on the learning side, I will collapse this and just say a learning task. You have some kind of data given to you to run a learning algorithm, and the outcome will be a predictor that can then be used on new data of this task. So this works very well. We've established methods starting from nearest neighbor classifiers up to deep neural networks that do this task pretty well. What also works quite well already is if you have multiple tasks to learn, to just learn each of them from scratch. You take data for each of them, you run a learning algorithm for each of them, and yet you get a predictor for each of them. And if you cannot afford that specifically because you might not have enough data for one of these tasks, then people have started to become good at what is typically called fine-tuning. So if you have a target task that you really care about solving, but you don't have enough data, you train a predictor on some other tasks that are called the source task that gives me some kind of trained model. And then I just use the target data to adapt this source predictor a little bit in order to lead to an adapted target model. So this is typically called fine-tuning, and it's basically the standard where you train many of the deep networks these days. But this is still a static task where you do it once, and then if you have a new task, you again have to train and so on. So what we're actually after would be continuously improving systems. So that is systems that I call them here lifelong learner, that they are challenged with a certain task to solve. For that, they give data and they produce a predictor that solves this task. Then they're given another task to solve and another one. And in the process, they extract information or knowledge from these tasks that help the system to learn better on future tasks. So to become more efficient or more accurate in future tasks compared to when they wouldn't have had the prior experience. So this very much models the learning in natural systems, which get better with experience, not just in a specific thing, but in a general way. So when you go to one of the machine learning conferences these days, you see a lot of related methods. So you see multitask learning, domain adaptation, online learning, that are all specific ways of transferring information between different tasks. Recently, there has been works on so-called meta-learning and lifelong learning, or class incremental learning, which are all minor variants of each other. And for each of these, there's a lot of new methods proposed, new training algorithms, new neural network architectures that are solving these. And in our group, and specifically in this talk, we concentrate on giving some kind of theoretical background to this. So not a new method that solves a specific problem, but more abstract general purpose properties of these tasks. So why will I talk to you about machine learning theory? Well, I think that theory can be quite useful. So if done right, it can keep us ambitious, it can keep us humble, it can keep us focused, honest, and essentially relevant. And I should say that by theory, I mean theory in the sense of machine learning theory here. So this is basically mathematical statements about abstract learning problems. It's not so much the theory of natural sciences where you would do modeling and so on. So it's not everything outside of experiments, it's more the mathematical side of theory. So what do I mean by all of these items? Well, theory can keep us ambitious because it allows us to formulate big goals. This is really the power of abstraction. So if you take an example such as reinforcement learning, where an agent interacts with a stochastic environment and it gets a reward depending on its actions and the state of the environment, where the goal is to learn a policy, these are abstract concepts that can be instantiated in many different situations. And over the decades, this has been used for a lot of different things, from playing computer games to balancing a pole to self-driving cars. So the underlying concept can be formulated in an abstract way, which makes it ambitious and last for a long time. At the same time, theory can tell us what is impossible. So if you can prove that something is impossible, then you shouldn't claim that it's true, probably. So for example, the famous no free lunch theorem by Lampert can be rephrased as that all classifiers are equally bad if you don't make additional assumptions about the problem. So any system that wants to learn from data must impose some kind of bias. There is no bias-free learning. And that includes not just specific architecture of classifiers, but this is a completely general statement. It includes neural networks, it includes the brain, it includes anything. It can keep us focused because it requires, in order to prove something about a statement, you have to think about the quantity of interest. So when you ask a random, probably starter in machine learning, well, what is the goal? What are you after? They will say, well, I'm given a training set and I want to find a function that makes as few mistakes as possible on the training set. Is this a good goal? No, it's completely trivial to write a function that does that. It just memorizes the data. So if you try to now prove properties of the system, then you will see that this is not a good goal because you do not get any guarantees about the future from this. Whereas properly formulated, you have a much better goal. Theory forces us to be explicit about the limitations and assumptions. If you want to prove that something is the case, you need to put in the assumptions. We already saw that without assumptions, learning is impossible. So we shouldn't just say there's some training data, but you have to explicitly make sure that this training data is sampled from a fixed but unknown distribution D. Then you have the IID assumption. And the IID assumption is often ignored, but it's one of the strongest assumptions we make in machine learning. So you better be explicit if you make it or not. Finally, you can argue about this, but theory can keep us relevant because it is there to last. So when you prove that something is mathematically true, it remains true. So there will not be a new architecture or a new data set that render what you proved before wrong. And this means that stuff can also stay relevant for a long time. Take boosting, which was invented in the early 90s. This is still underlying a lot of of modern methods of machine learning 30 years later. So hopefully I've convinced you that theory is something worth looking at. So now for those of you who are not experts in machine learning theory, let me give you a quick refresher. So we are going to study statistical learning theory. We don't care about computational aspects. And a learning task is just a set of possible inputs, for example, all images, a set of possible outputs, for example, a bunch of labels, like is it a cat, is it a dog, is it neither of those, and a loss function that tells us how good is any prediction we make compared to the true one. So this curly L of some y and y prime means if I predict y prime, but the correct answer would have been y, what kind of loss does that impose? And in the easiest, you just check if your prediction was correct or not, and then you have 0-1 loss. So the x and the y are connected to each other by a probability distribution, a joint distribution over x and y. And you can also think of this as a distribution over x that tells you how likely is it to observe any specific input, and a conditional distribution of y given at x that says if my x is fixed, how likely is it that any of the y's is the correct output? And if you don't like the probabilistic aspect, just think of the y given x as deterministic. So for each x, there is a correct y. And then the joint distribution is the product of the two. So the goal is now not to minimize some training error, but the real goal is to find a predictor from x to y that will work well on future data. So formally, that it should have a small risk, which is the expected loss. If I'm given a new example that is sampled from the underlying probability distribution, that is an x and a y, I apply my predictor to the x, I compare it to the correct y, that gives me some kind of loss that I suffer, and I want that the expectation over this loss over the data distribution is as small as possible, and that I call the risk of the predictor. We cannot compute this, but it's a mathematical object that is the real goal of interest. So here's the summary of the main parts: an input set, an output set, loss function, a distribution, and the goal is to find a predictor with a small risk. Now, the standard setting how to do actual learning is batch learning. You're given a training set which consists of x, y pairs, so input and correct output pairs that themselves are sampled independently from the data distribution D. And now, for any particular predictor that we want, we can evaluate the empirical risk. So meaning we compute the loss of our predictions on all the training examples that we have. So this is now a computable quantity. And statistical learning theory is mainly about studying the connections between the true risk that we cannot compute and this computable approximation to it. If these two quantities are similar, the real risk and the empirical risk, then minimizing the empirical risk is a good learning strategy because it's so close to the true risk. So a classic result from statistical learning theory would look like this. You have a generalization bound here in simplified form, where if you have a certain set of potential predictors that we call the hypothesis set, and you're given a set of n training examples sampled IID from the true distribution, then it holds the following inequality that for all predictors in my class, the true risk will not be bigger than the empirical risk plus some term that is the square root of the complexity of the hypothesis class and the number of data samples. So I call this a simplified version because the quantity on the right of this inequality is actually a random one because the training set is random, so the empirical error is also random. And this statement holds really it holds with high probability over this training set. and the dots hide these additional terms that guarantee that you can achieve this with arbitrarily high probability. But for the interpretation of these, the high probability doesn't matter, so I just always leave it out. So just as an example, if your hypothesis set is the set of all possible linear classifiers in some d-dimensional vector space, then the complexity will be d+1. And as long as your number of samples is bigger, large enough compared to the dimension, you get actually decent guarantees that real risk and empirical risk are similar to each other. On the other hand, if you have a much bigger class, like all decision trees, the complexity of this will be infinite, and this theorem doesn't give you any guarantees. So specifically for this talk, we will not make use of deterministic, but of randomized predictors, because we want to work in the framework of PAC-Bayesian learning that I'm going to introduce to you next. So to think about randomized predictors, first think of each of the classes of predictors, each of the models that we want to learn as parameterized by some vector. So if it's a linear model, this would just be the coefficients of the linear combination. If it's a neural network, it would be all the network weights together, and so on. And then we can define a probability distribution over this parameter set. So if you take a uniform distribution, then all possible parameters are equally likely, meaning all possible models are equally likely. We can also define maybe a Gaussian distribution, which is sent at a certain location, which will tell us that parameters close to this mean mu are more likely than parameters that are far away from this mu. And you can also make this deterministic and just make your model a distribution, a delta peak at a certain location. Then only the classifier with parameters θ0 has any probability, and all the others have zero probability. So any distribution over the parameters induces a randomized predictor, where if we have any kind of input we want to make predictions for, we first sample a parameter according to the distribution. That gives us a corresponding predictor, and then we evaluate the predictor at the input that we're interested in. So this will be a random output, because it depends on the random sample theta. And we can evaluate this for all possible parameters and compute the expected risk. So the risk of a randomized classifier is the expectation over the risk for all the deterministic classifiers according to the distribution of how likely these deterministic classifiers are under the distribution Q. That works for the true risk, and it also works for the empirical risk. So PAC-Bayesian learning is a framework that allows you to elegantly reason about learning and prove some amazing theorems. So learning for these randomized predictors corresponds to updating our beliefs, which hypotheses are good and which are not. So we start with some arbitrary probability distribution P over the parameters that we call the prior. Then we will observe a training set. And then we update the distribution Q. We create a new distribution Q that reflects our updated belief, what we think are good predictors for this task. And clearly this switch from prior to a posterior resembles the Bayesian paradigm, but it's more general than that, because the step from the prior to posterior doesn't have to be based on Bayes' rule. So you can use any way you want to go from P to Q. And the prior and posterior is just for analogy reasons. We also don't need a likelihood or data generating model for this. So the strength of this framework is that you can prove the PAC-Bayesian theorem. There's, again, many of those. Here's a version from McAllister in '99, which states that the expected risk, so the risk of any of these randomized classifiers that you create after seeing the training data, is not bigger than its own empirical risk, plus a term that contains the square root of the Kullback-Leibler divergence between the prior and the posterior, where this measures the difference, how different the posterior that we chose is to the prior that we started with. So this inequality holds for any possible Q that we could choose. So which one should we choose? Well, the most promising is the one, we want one which has a small risk. So since this gives you a bound on the risk, the best choice might be the one that minimizes the right-hand side of the inequality. So that will give us at least the one with the smallest upper bound on its risk, where the risk itself we cannot compute. On the right-hand side, we might be able to compute. So just again, a simple example, imagine that your model is parameterized by theta. And now we start with some kind of prior distribution. Let's say we use a Gaussian that is centered at some location mu0. Now, after seeing the data, we could switch to a different location. So we could switch to any Q that has a different mean, for example, mu. And then we know that the Kullback-Leibler in that case will just be the squared Euclidean distance between the mu0 where we started and the mu where we ended up. So plugging this into the theorem gives us an inequality that says that the true risk of any of these q's will not be bigger than the sum of two terms, which is the training error, so the empirical risk of this, plus what came out of the square root of the Kullback-Leibler, which is just the distance between the mu that we actually use and the mu that entered the prior. So you can also think of this just as minimizing the right-hand side now means to minimize a training loss plus a regularization term. So this just recovers the standard way of how we train many classifiers, training error and regularization. So if you look at this, you also see that the Kullback-Leibler is divided by the number of samples. And that means that if we have a good guess for the prior, meaning we don't have to move far away from the prior to get a classifier Q, then we need less data. So having a good prior means less data gives us still strong guarantees. So clearly this is something we would like. So imagine if you have a neural network that you now want to classify. If you just put a uniform prior on the weights, then there's no constraints at all what we will choose. I mean, there's no guidance what will we choose as the Q. If we put a Gaussian prior, then the Kullback-Leibler divergence will just be the norm of the mean of the parameters theta that we get, which means small norm parameters have a higher probability than large ones. So probably we would like to find a network that has small values and still explains the data well compared to big ones. So, and you can also make this more extreme. So if we put a delta prior on some of the parameters, for example, the parts that compute the features, and a probabilistic prior on the rest, so the ones that define the classifier afterwards, then this would just mean that in order to get bound, we have the part of the parameters frozen at the initial values, and only the remaining classifier weights can change. So you have a lot of freedom in how you choose your prior, and this expresses different ways what you want to penalize in the learning. Now, how should we actually set the P in practice if we don't have much else to work with? So the one constraint of the theorem is that the prior may not depend on the training set S that we use to choose the posterior afterwards. But we can use any prior knowledge we have about the problem. So the three options I just showed you, these are just might reflect just prior knowledge we already have. We can also make it data dependent as long as the data isn't dependent on the training set S that we afterwards use for choosing Q. So for example, later we'll see an example that you can take. If you have data coming in the stream, you can take the beginning first samples to come up with a prior, and then the remaining samples to update those to the posterior and still get some guarantees. And finally, you can also use other data from other tasks in order to come up with a prior. And this is what I'm going to concentrate on in the rest of the talk. So we want to, in the situation where we have many tasks to solve, we want to use some of them to be more informed about future tasks. So as a reminder, multitask learning would be that we get many tasks to solve, and we want to solve them at the same time. Each of the tasks is a data distribution, and for each of the tasks, we get a training set according to that data distribution. The goal now is to find one predictor per task, such that the overall risk or the average risk, according to the individual distributions, is small. So can we use this to extract information that is useful for future tasks? Not so much. So the task could, in this framework, can be anything, right? They don't have to have any relation between them, and there might not be any future task. And even if there is some kind of next task coming up, it might be completely unrelated. So take example where the first three tasks are playing tennis, badminton, and squash. Then if you infer something from this, then probably that you should concentrate on holding a racket and moving your arm a lot. But then if the next task is unrelated, such as solving Sudokus, then this prior of moving your arm a lot and holding a racket will probably hurt you rather than helping you. So this is an effect of negative transfer. And the big question is, how can we avoid any of this negative transfer? Can we find conditions under which negative transfer is not going to happen? So what I'm going to tell you about is two scenarios that allow this. So one of them is meta-learning or meta-learning to learn, and the other is lifelong learning or online multitask learning. There's alternative settings, of course, where, for example, before you transfer, you infer the similarity of which are the similar tasks. We ourselves have done some work on this, which I cite here, but of course, there's much more available in the literature. Let me start with the meta-learning. So this is based on a famous model by Jonathan Baxter, which is the learning to learn scenario. And the main assumption we make here is that the tasks are not arbitrary after all. So instead, there's a task environment that I call capital or curly T, where you have a set of all possible tasks and you have a distribution over them. I mean, these are not explicitly given, but we assume that there exists a set of all tasks and a distribution over them. And then the observed tasks are just samples from this environment, independently sampled. So for example, the task environment be all possible people in the world, and then each of them has a certain probability to visit a website, and then the users who actually visit the website are just a random sample from the ones that could have. For each of the tasks we have, it has its own data distribution, and we get a training set from this data distribution. For example, if the user is on the website anyway, he or she clicks on a few ads, and this is our training set. So now the goal of meta-learning is to take these available data, so the available training sets, in order to construct a new learning algorithm. So you want to build a learner that takes as input a training set, so a tuple of inputs, outputs, a number of, many of them, and it outputs a predictor that can be used to make predictions on new data. And this learner should work well on any future task it is given. So if you have a new task that is like T star that is now sampled according to the same task environment with the distribution D star, and we get a training set from this, then the learner applied to this training set should be a good predictor, meaning it should have a small risk. Right? So it's really a meta stage where you have a learning of a learning algorithm, and then the learning algorithm itself is applied to a new learning problem. So the first result I'm going to tell you about is by my student Asya, or former student. She's now working at Bayer in Berlin. And it's called PAC-Bayesian Framework for Lifelong Learning. So the first result we have, assume the following setting. So assume that we have some kind of fixed learning algorithm that gets as input the training set, and it also gets as input a prior distribution over the hypothesis in this random framework we look at. And the output is a randomized predictor, so a posterior over the distribution, a distribution over the hypothesis. Now, for the learning step, we first fix a prior distribution, and then we observe a number of training points, training sets from different tasks, which were sampled from this task environment. We apply the learning algorithm to each of these with a prior P, and that gives us posteriors, so randomized predictors for each of the tasks. And the theorem tells us that for any new task that we haven't seen before, if we do this, the risk of the resulting posterior predictor on this task will not be bigger than the average of the empirical risk of the task we have seen before, plus the Kullback-Leibler between the posterior and the resulting posteriors. So we now have a way of quantifying how good will this method be on a future task, even a task that we have never seen before. The problem is that this is how good the prior worked for that, but the prior must be fixed before we see the data. So we cannot, now that we know how well each prior works, we cannot adjust the prior based on the observations we made. So it has to be fixed ahead before seeing the data. That means we cannot influence it using the data. So this was the first problem on the road to lifelong learning. And the way we overcame this is by, again, remembering what learning in this PAC-Bayesian framework is to mean. It means updating our belief about things. So in order to actually learn what priors work and which ones don't, we cannot learn a fixed prior, but we can just update our belief into them. Meaning we will now have a distribution over priors that I call a meta-prior. So this is a distribution about priors that we fixed before seeing any data. And then we can use the data sets to update our belief which priors are good and which ones are not, into a meta posterior, which again is a distribution over priors, but now one that reflects what we have learned from the tasks. The learning step is still, for any task that you want to solve, you sample first a prior from this distribution, then you observe the training set, and then you compute the posterior of the predictors by applying your learning algorithm of the training set and the prior. So the resulting theorem is the following. So we can now quantify for any new task T star that you haven't seen before, the risk of this procedure in expectation over the priors is not bigger than the average of the training risk that you've seen in the tasks, of the tasks that you've seen, plus equivalent library between the meta prior and the meta posterior, and the average of the priors over the individual learning task in Kohlberg-Leibler divergence with the posterior. So let me just go through this more clearly. This is an inequality that holds for all possible distributions over the priors. So we can use this to learn what distribution over priors is the best one. And that we can do by just minimizing the right-hand side as long as it's computable. And that means we have to minimize these three terms. The first is the expected training error on the observed tasks. The second is a per task regularizer because it measures the Kohlberg-Leibler between the prior of each task and the posterior of each task. And the third one is a regularizer on the meta level that says that the posterior we actually choose over priors later shouldn't be too far away from the prior we had before across all tasks. So the insight is that meta learning is actually possible. You get guarantees, but you will have to impose regularization on the meta level. So there's a concept, basically a concept of meta overfitting if you don't do that. So the reason we were able to achieve this is really because the Baxter's learning to learn says that tasks, observed in future are related to each other because they are all samples from the same task environment. Sometimes this might be an okay assumption. So if tasks are random customers that visit a website, this might be fine. But often it is not realistic. So tasks might not be independent. So for example, if you have users in different time zones, then certain kind of users will show up at different times than others, and you do not have independence. Also, the task might not be identically distributed. So for example, instead of solving a random game every day, maybe you want to solve games of increasing difficulty, and then you would not have the identical distribution assumption anymore. You can weaken the assumptions of our results a bit. So you can introduce dependence between tasks, and you can also give them some kind of continuously changing property. But ultimately, if you want to generalize from observed tasks to future tasks, you will always need some kind of law of large numbers argument that says you can make a statement about a future task because you've already seen enough similar tasks in the past. So in order to overcome that limitation, another former student of mine, Alex, worked on multitask learning, but now in an online fashion. So that means we're still having an input set and an output set. We still have a loss function and a hypothesis class. But the tasks we want to solve now are a sequence, and we do not make the assumption that there's an environment or that these are sampled according to some distribution or related to each other in any way. The goal of the learning system is to learn the tasks sequentially. So at any time t, we observe a certain training set according to some task distribution, and then the learner has to output a predictor, or in our case, a randomized predictor for this task. And the quality of the predictor, as always, is measured by the risk. And the goal is to achieve an as small as possible average risk up to any stage t. So over the first t tasks, the average risk of our predictors. The main idea of this work is that we get inspired by online learning. And in online learning, the data is just a sequence of data that we don't make any strong assumptions about. So in this case, we take the data of all tasks and we treat it as one long example, one long sequence of examples. And we update our predictor Q at each individual sample. And if there's the training set of one task stopping and the next one beginning, we don't consider that at all. We just ignore if there's task boundaries. So that gives us a long chain of predictors at every individual sample. And if we want to have a solution to an individual task, we just use an online to batch conversion that takes, that is a classic method from online learning, which allows you to take this sequential sequence of predictors and turn them into one, hopefully better total predictor. So the algorithm expresses exactly that. We start with an arbitrary prior distribution, and then for each of the tasks sequentially, we don't have to know how many it is. We receive a data set, and then for all samples in that data set, we always update our posterior by a small step in a proximal point algorithm. Then after we've seen all the samples and processed them, we compute a predictor for the task itself by averaging the posteriors of all the individual steps. That's the online to batch conversion. And then we know that there will be more data coming from the next task, and we choose as prior for the next task the last posterior we had for the current task. So then we are ready to receive the next data set, process it sequentially, and so on. So this is an easy algorithm, easy to implement, but it has some nice guarantees. So in particular, if you look at the sequence of solutions, predictors produced by this algorithm, so Q1 hat up to Qt hat are the ones what the algorithm output on the first T tasks, then it holds that the average risk over these is not bigger than the average risk of any other predictor Q, plus a term that includes this KL divergence between the posterior, between any other Q and the prior that we started with, divided by the square root of the number of tasks times the number of samples per task. So the first observation is that when the number of tasks go to infinity, this additional KL term on the right converges to 0, even if each task has only finitely many samples. And this is in contrast to almost all other bounds, which typically need, in order for convergence, we need not only that the number of tasks goes to infinity, but also that the number of samples per task goes to infinity. And that is, of course, a much less realistic assumption because, I mean, for any reasonable task, we only have finite data. So one caveat in this is that the right-hand side of this compares a single randomized predictor for each task. So it checks how well would any individual predictor have worked across all the tasks that you've seen so far. Now, if all the tasks are very similar to each other, then this is a strong baseline because maybe there's one predictor that works well for all of them. If they are all very dissimilar, then the quantity on the right is bigger than it would need to be, and the guarantees are not very strong. So this is the main limitation of this online view we have. Now, the difference to Baxter is clearly that we have an arbitrary sequence of tasks, so we do not have to assume that they are sampled from some task environment. At the same time, the statements we get are of a different nature. So instead of saying we can now control how well our method works on the next task, we just know that the average across all tasks will be reasonable. So in particular, in this sequence, the next task might be completely unrelated, and then in expectation of the learning to learn setup would not hold, but we are able to do this average risk, we are still able to control. So the algorithm specifically gives guarantees no matter what your tasks are. So that's a good thing. You can prove this without having to assume some kind of relation between tasks, but it's clear that if the tasks have no relation or only a weak relation to each other, then it's not a very strong guarantee you get. So you can make this more powerful by, for example, introducing multiple sequences that only work between tasks that are sufficiently similar to each other, and we have that in the application. But ultimately, there's no magic bullet. So if, for example, all tasks are completely dissimilar from each other, then there's no mechanism that would save us and work. I mean, if there's no information that any task shares with each other, then we will also not be able to benefit from having seen other tasks before. So that is just a fundamental fact we have to live with. So this brings me to the summary. We looked at two scenarios for transferring information between tasks. One is the meta-learning, where you try to learn a learning algorithm, and one is the lifelong learning, where you solve the tasks sequentially, extracting information on the fly. It was a theoretical view. I mean, we proved theorems, and what ideally comes out of theory for me is that you get a more clear picture of what you actually want, what is possible, and what is realistic. So we did derive some algorithms that do have theoretical guarantees, but ultimately there's more open questions now than there was before. And with that, I would like to thank my research group at IST Austria, as well as the alumni who did the work, in particular Asia and Alex, my funding sources, which is next to the IST, also the ERC. And now, if possible, I'm happy to take questions.
Thanks a lot, Christoph, for the very masterful and very relevant talk today. We are awaiting some questions. In the meanwhile, While they are asked, I can probably start with some that I have. So
Okay.
I'm actually, as you know, from a background more from computational neuroscience.
Sure.
And so I'm, of course, more interested in the applications there. But before I go to that itself, maybe I can ask you, do you, for example, if you were to actually to practically train a network, would you also give the task identity when it
What's the
was
task
being trained?
identity? So you mean tennis? Is that a task identity?
Yes. For example, if you were to learn tennis, badminton, and squash, while learning tennis, would you tell the network by some external input, by an extra input, that now it's learning tennis and now it's learning badminton, or it has to, or that's not important?
I mean, I think there's many different ways. So if you just say this is task 1, this is task 2, this is task 3, then information is rather limited. But at least you know when you might want to, I mean, transfer or not, right? So the ones I told you about, they don't have an identity. They just, you know that the new task begins now. What is much more important, I think, at when you want to solve, I mean, at prediction time, when you solve a task, do you know what you want to achieve? Do you know that this is now tennis again, which you learned previously? Or do you just get some input data point and you don't know which of all the old predictors you went to apply? So I think it makes sense that if you want to play tennis, that you know it's tennis at prediction time. How you actually call the tasks, I don't think that makes a big difference. So I call them 1, 2, 3.
No, that's no. I meant that's fine. That's just a label. But yeah,
So,
essentially the information should be given to it, especially at prediction time. That's the key thing.
I think that, I mean, if the information is there, it should be given, right?
Yes.
If you don't know what you're doing and you just, somebody gives you more and more, I mean, of course you can come up with ways where you don't know if it's a new task or not, or what you're actually, I mean, if you just get data from all tasks and you give you random examples
Then
from
it's
random
just
tasks,
one task, effectively.
seems very, I mean, hard, and it's hard enough already.
Yeah. No.
Right, that said, I mean, people have used the task identity really in the sense of the name. So tennis versus badminton versus Sudoku. And in order to infer some kind of similarity between tasks. So you can use word embeddings, you can all kind of natural language that if you already know the name of the task, you might already know what is more related to what else. We don't use that here.
Yeah, the similarity is a very interesting idea as well. I would like to ask further on that. But before that, there are others who want to ask. It's more important. We will invite, so I'm going to invite Mauricio on screen. He's a senior lecturer at the University of Sheffield, if it's the same Mauricio Alvarez that I know. Let's see, I'll invite him here. And he is asking the question, let's see if he can just come on and then he could ask it himself. If not, I will ask for him. Yes, we have Mauricio.
Hi,
yes.
Christoph. Great talk. So yeah, I just wanted to ask if you are aware of similarities between this framework and something called variational optimization.
Yes. So there is a relatively close connection between the variational learning of neural networks, for example, where you have all these elbows and so on. This looks very similar to the KL term in the PAC-Bayesian bounds. So this has been explored, and I think, I mean, they are pretty similar. I mean, the PAC-Bayes, it gives you specific constant and specific terms in order to have an upper bound, whereas the optimization, typically, it's just a transitionary step to go to some kind of minimizer or something. But yes, there is connections, definitely.
Right. And the other question I had was, so how, I suppose that trying to find those posteriors, how complex is the optimization will depend on the type of posterior that you assume, yeah?
I mean, it's not that I'm proposing to use this algorithm explicitly, right? It's, I mean, inspired by theory, you can always do something slightly different. But no, the good thing here is that you do not have to compute the true posterior. Right? So it's not like Bayesian where you have one correct answer. You can choose any posterior you want. It will hold, but some of them will have a better guarantee than others, right? So typically, if you have this kind of loss plus regularization, then all you have to do is run your regular training with some additional terms, for example, as penalty on the norms, right? So that would be the same as what you would have been doing anyway, maybe. And that's also what people do in fine-tuning, right? You start at a certain location, and then you just move a little bit away using the loss. So that is not particularly different. If you have much more complex models, so one we did is, in the original paper, it was linear models, and the prior we learned was a subspace. So you have a high-dimensional space, and you want to know which subspace of this is the most promising. And then you need to do a little bit more work, because you have to like update your knowledge about subspaces. But ultimately, I mean, it's up to you how you parameterize prior and posterior in order to make it, on the one hand, powerful, and the other still computable.
Okay, thank you.
Right. Yeah, thanks, Christoph, for that. So while we wait for any further questions, I'd also like to ask another one, which is, so you have these two paradigms: meta learning, where all the tasks are kind of given at once, and then you test on a new task, versus continual learning, where tasks are sequential. But in general, I mean, for, let's say, for humans or whatever, for animals, the tasks come interleaved. And so does the sequential learning, for example, already handle this? Or, for example, does sequential learning cover meta learning? Is meta learning a sub problem of sequential learning? Or, if they are interleaved, can sequential learning still handle this kind of? Yeah.
We didn't look at the interleaved case, because yes. So it would, I mean, the meta learning as people do it currently would typically be like a real batch, right? You're just getting all the data, and that's all you will ever have from these tasks, right? The lifelong, the online multitask is much less explored, I would say. If you have task identities, then especially the algorithm we had, it just learns sequences, right? So if you get data from a previous task again, and you know that it's a previous task, you might continue the sequence of that. And you just keep multiple hypothesis distributions around. So that wouldn't be, I mean, surprised. It can stop anytime and then start at any time. It might be much more practical problem. So if you want to do this with neural networks, then you come suddenly into the problem of catastrophic forgetting and like the real world. This is not covered here, of course, right? So this just says minimize something, and it doesn't, or typically it would say once you've created a predictor, you just freeze it, and you don't continue learning on this specific predictor. So catastrophic forgetting happens if you have something learned, but then you continue learning, and there's interference with what you learned before, which of course is what brains would do, but the theory here would just freeze and continue.
So if I understand correctly here, essentially the next task you would learn on a different predictor. So this would not be on the same network, I guess. No,
you wouldn't have. I mean, this more or less would be you learn a predictor, and then the mathematical is the function, and then this function is stored and used whenever you want to solve this task.
Right.
And the next, you can use this as initialization for the next, but you would start a new. I mean, practically you would have to start a new network for that, or rather, you save the weights and then continue. But if you want to solve the previous task, you just load the weights from disk again. So it's not like one big system that learns everything holistically. That we are still far away from solving. So we don't even know what that would actually mean.
Yeah, I mean, you already answered that, but I was just going to probe you a bit further on what one can say from this about catastrophic forgetting and
catastrophic forgetting, people have noticed that it exists. And people claim that they solved it every year 10 times, but I mean, I don't think that it's solved in any kind of way that makes, that systematically makes sense, right? So there's methods that try to solve it by not moving too much anymore, but then you're not flexible enough to learn really new stuff. And there's methods that try to rehearse with old data, and then you have to keep old data around. Or you need to learn a generator of old data, but all of these are kind of, I don't know, hacks.
Yeah.
Sorry.
This just reminds me also there's work from Michael Halassa's lab, with whom I also worked, which was on that mice apparently switch networks, so they can use the thalamus to switch sub-networks within the prefrontal cortex based on the task. And they can even learn the identity of the task in the thalamus, and based on the identity of the task, they switch the network to be used. So I was actually wondering if, for example, you said you have a way of automatically finding the similarities between tasks. So it would be interesting to see if for similar tasks, one uses the same network, and for very dissimilar tasks, one switches networks. So I was just curious to know more about this, how to find similarities between tasks and so on.
So, I mean, there's a big chunk of work on defining similarity between tasks, and most of them are, let me just try to find the ones, just to, shamelessly advertise again. Where is it? Oh, so, okay, maybe it's gone. So one thing is you try to learn a predictor on the, you try to reuse one of the old predictors to solve the new task. And if that fails, then probably it wasn't similar enough. You need some kind of threshold what failure means, but that is one way that the student Asya had, for example, in NeurIPS 16. You can also compare the solutions in terms of the weights of learning both, and if the parameters are similar. That works well for convex models where you have unique predictors. For neural networks where you have many different parameterizations of the same function, you shouldn't really compare the weights in order to determine if it's the same function or not. What we did most recently is that you compare the actual data of the tasks to each other if you have it available. And that is because if you have a proper measure of similarity between the data sets, then you can guarantee with the right distance measure that learning on one will not be too bad compared to the other. So this is what comes out of domain adaptation, where if your data set you train on is not the same that you later want to use for evaluation, the distributions, then you need a measure that says if my data sets are similar enough, the learning will also not mess up. And that's a relatively strong criterion that most of the more heuristic measures don't have.
Cool. Yeah, no, that's already quite some ideas which seem quite relevant for this topic as well in computational neuroscience. So that's great. So there are no further questions as from what I can see. And well, we thank Christoph again. This was an amazing talk, very clear. I learned a lot coming from a slightly different background. So hopefully we will see you again soon. And thanks again, Christoph.
Thanks for having me. Bye.